So if you see the presentation, then I will just start working my way through it now.
Thank you.
Okay. So as Chris said, I'm the founder and president of Coherent Technologies. We're an innovative company, a great follower of Gary Pratt's object-oriented industrial programming techniques. We love that because of the speed of application, the reliability. There are just so many positive aspects to what Gary has created and is encouraging us to embrace. I have a couple of examples where we used his object-oriented techniques with sections of pipes, automatic routing of fluids between different sources and destinations. I'm going to go through this very quickly and just in the interest of time. And then later, those same objects were extended to prevent isolation of a pipe after the transfer was complete, since these were heated pipes that would had burst in the past because of being blocked in without a way of escape. And that all worked flawlessly. And for some reason, oh, there we go. There it is. Okay, so we're a company of innovation. And this innovation, our own innovation, is born out of our inherent love for innovative technologies. And the small modular reactors and the microreactors are an innovative approach to nuclear power that offer many, many, many benefits of somewhat akin to the object-oriented work that Gary has done, in that they create a specific smaller modular objects, reactors, that can then be extended to meet whatever size demand is needed by just adding more reactors. But they're cookie cutter, built, tested, reproduced, built in a factory, and just pushed out the door for use wherever the power is needed. The microreactors are even truck mounted, so they could be quickly mobilized to a location that had a particular need, such as the Carolinas right now. Texas A&M University is one of the leaders in this field and established a center for the advanced small modular and micro nuclear reactors. Dr. Hassan is quite an innovative leader in this field in nuclear, and you can just read some of the benefits off to the side of why small modular reactors and microreactors are becoming so popular. And the university wanted to create a test bed to test and verify control technologies and modeling applications and such. So this is just an example of one of their first ones that they're putting together, which is in the process of being fabricated now. The control system is already there, waiting now for the piping and sensors to be connected. And this was their first. Excuse me. This first test bed was a relatively small one, but it will establish the principles for larger and future ones. So their objective was developing this test bed that can be applied to different sizes of reactors And as a proof of concept where they can, can test this in a safe, controlled environment, but in a realistic way, using modern technology, modern techniques for the controls. So they'll have both the physical control platform, a digital twin model that they are creating, and then use that model to make supervisory control changes to the reactor operation. To reach these objectives, the physical control platform, as you can imagine, needed to be first and foremost secure, but also future-proof, because we are in a evolving area of cybersecurity, and technology development is not slowing down, it's just speeding up. They needed high performance so that the modeling could be rigorous dynamic modeling, and also support advanced control capabilities. Reliable, of course, that's a critical situation, critical need in a system, a nuclear system. But we want to leverage the developments that are already there in the commercial and cellular networking systems. So as opposed to trying to reinvent the wheel. And on top of it all, it would be great if it was economical and adaptable by being a software-defined system built on commodity hardware and operating systems. So after a review, the COPA control system, using in this particular instance, the style IO was chosen as the best fit for this project. So COPA is a coalition commercializing the open groups, open process automation standard. Install, so they're who's providing the hardware and the system implementation. The stall IO was delivered by stall, but any component in the control system, because it is so modular and software standards based, could be interchanged in the future for future designs with very, very, very low risk. To put together the best team for this, we selected Seaplane as the supplier of the COPA system. They're one of the members of the coalition, and CSI, which was one of the founding members of COPA, to provide additional consulting services. And this is the physical system. Phase one is first delivered. The spare space for future, it has you can see the DCN compute node is a standard industrial PC. And the IO system is the style IO, but rather than running the logic in the style brain, it is being used as an industrial IO data server using the OCF communication technology to do secure communication to the DCN compute node, which is doing the actual control, running the CODESYS logic. And the industrial IO was just wired back to some terminals in the backs, because labs are notorious for having a lot of changes to which signals go to which channels and such. So we gave them plenty of real estate in the back for making those changes. And down at the bottom, the advanced control platform is where the VMs are running for the advanced process applications, the engineering workstation, all those functions, the historian, and the graphical interface. Now, this architecture, getting into a few more details, is the IODCN this is the particular model of stall that was used, and the communicating with the compute DCN. The compute DCN is an ASRock industrial PC running the Ubuntu operating system and Docker containers, which are running the CODESYS runtime and the Python model that the university is developing. The advanced control platform is on a very capable Supermicro system with which is running multiple VMs for the ignition gateway, the engineering workstation, and it shows there, we list the operating systems and choices and such that were made there. The historian and the GDS, which we'll talk more detail about in just a little bit. That is an amazing piece of technology in itself. The stall configuration is very straightforward, web-based tool, first for monitoring that you can drill down into to monitor the operation of the I/O as it's just a diagnostics tool. It is configured using their standard FDT application, which allows you to drill down into specific objects and configure them, all the details related to those. And then another tool that is used during the course of a project is a tool such as UA Expert, that allows you to go in and monitor or even make changes to specific settings within the sorry, my brain, I'm having a moment here. The open process automation system. So this is the CODESYS project on the compute-only DCN. This is, I'm going through this very, very quickly. The input processing, there are three major sections to this. There are a huge amount of libraries and such are provided by the COPA organization as a part of the implementation, the detailed implementation of the to the standard, to the process automation, open process automation standard that maintain the fidelity and the compliance with the standard. So as the implementer, as the systems integrator, they have greatly reduced the demand on our work in interpreting and understanding the process automation system, open process automation system. The first task is the input processing. So as you can see there, the calls to that when you define the variable, that is all that is necessary. Much like Gary's object-oriented programming, you specify these objects were very well created, and you specify the different parameters for them. These are the analog inputs, digital inputs. There's some temperature inputs and such, and then that brings it into the CODESYS system, where it can then be transferred to variables, tags that, again, have a matching data structure. So it's easy to then transfer that to tags with tag namings that is relevant to your system, to the project. Then the exchange, in this case, they had named this the exchanger algorithm. So it has a control blocks where those instances then of the analog, like the analog input function blocks and such, are linked to those data structures, the tags. And this is where it comes down to the tag that will be exposed to the rest of the world for graphics and such. After doing the control functions, then it is pushed back out easily to the control hardware, essentially by reversing the process. Now we'll be outputting analog outputs, digital outputs, and such from the system. Now, where it starts to get really interesting, of course, then it's published using in this case, we use the symbol configurator to publish this to OPC UA, which was just as simple as just exposing those blocks. But behind the scenes, and that graphic doesn't look. It did a bit of an overlap there. But behind the scenes, the control application development was easy, but because of this global discovery GDS. So I'm going to skip through that. And this gets down into some more details of what the GDS does for you. It meets some OCF, which OCF is the Open Process Automation System Communication protocol for secure communication between different nodes. It requires time synchronization and uses the IP-based message transport. So the OCF each of the nodes will, as in Gary's case, will register themselves with the GDS so that it knows where they are, exactly where they are, and the application does not need to know where those objects are, because it will simply go to the GDS. Its function blocks will go automatically to the GDS, find the full path name and path to that data, and update and start the data transfer. The GDS also has a critical role in security, authentication, and authorization. It is the part of the system, of the open process automation system, that manages and accomplishes the authentication between servers. For example, client A has read-write for all nodes and tags, but client D has read-only access to nodes and clients, and that is managed through the GDS. encryption and trust is also managed through the GDS automatically. The list have to be created, of course, but by the user to define what he wants the white list or the trusted list to include. But once that's done, the GDS manages the keys and keeps that up to date and prevents communication goes by what keys have been shared with which nodes. And it also handles the certificate provisioning. So it actually manages because certificates expire, so it automates the generation of certificates, stores the public keys in a local database, and pushes the trust list to the clients and servers using push communication. And while we did not use it in this application, it didn't need it, but orchestrators can automate the trust list as part of a deployment and management of applications. This made the creation of the ignition HMI very straightforward. We created UDTs by simply browsing to the control system, dragging that over into ignition, and automatically creating a UDT based on that structure. We then went in and customized that to make each, this is a one-time effort to customize it, replacing the chosen instance value to be now linked to the instance tag name. So this ensures that if you call it motor 1 or pressure transmitter 101, that it really is linked to the correct object over in the control system. Templates were also created for visualization that were based upon those UDTs. So the end result of that is that this screen on the left was simply 4 template repeaters, and that repeated those templates for all the variables that were in this specific first phase project. And we only had one other object to put on the screen other than the A&M logo, and that was the emergency stop status button, but everything else was automatically linked. And since the UDTs also define the data history that was desired for each type of point, the data immediately upon creation of the tags began collecting. And this was very much a collaborative effort with multiple parties. The Department of Nuclear Engineering at A&M is managing the Python script, the Python model of their system, and working on the digital twin side of it. Coherent Technologies assembled the system, put the pieces together. Seaplane provided the physical hardware, the cabinet itself, and CSI is advising A&M on their use of the model and interconnection of it with the control system. So that was a very quick blast through that, and I appreciate your attention. And